let's talk about Chapter 8 in our textbook, X-ray machine circuits and generators. And this will definitely flow from Chapter 7 as well. There's some stuff in Chapter 7 that we kind of started unpacking, but we didn't quite finish, so there's a lot of, we're going to be doing some flipping back and forth to make sure we understand all this material. Okay, so we need to be able to identify the major parts of the X-ray imaging system, and Tom sometimes talks about this as like the Fisher-Price model of the X-ray tube, right? That we're going to look, we just want like big picture items, how the circuitry works to power the X-ray tube. Now, if you were to look at the actual circuitry inside of an X-ray tube, it's much more complicated than what we're actually doing, but we need to label those major parts. I want us to be able to draw a diagram of the X-ray circuit. You'll see kind of more of what that looks like here in just a minute. I'm not a big fan of the diagram that's in our textbook, so I may use the diagram from a different textbook, but regardless of what kind of diagram we're looking at, we should be able to orient ourselves to that circuitry. We need to talk about what each part of this circuit does and why it does what it does. Each thing is important and integral, and if any part of it stops doing what it's supposed to be doing, the rest of the system kind of falls apart. We'll talk about power waveforms and how they relate to generators, which that is definitely something that interfaces with Chapter 7. And then we'll wrap it up by talking about exposure timing. So the automatic exposure control is also part of this circuitry. So in terms of like kind of big picture, like if we're at that 10,000 foot level, the imaging system, there's kind of three parts to it. There's the operating console, there's the high voltage generator, and then there's the X-ray tube. And so I like this way of organizing it. This is the most simplified way that we can talk about the circuitry, right? Is to break them up into these three sections. And it's important to think about them in these three sections because you will receive registry questions that are asking you to think about them in these three sections. So the operating console, this is the part that you actually are inputting information in, dialing in the KVP or the mass, selecting a focal spot, and then actually depressing the button to expose the X-ray. That's the operating console, right? So it has things like KVP selection, MA selection, time selection, all of that there is on the operating console. The exam type selection is on the operating console. It is considered a low voltage part of the X-ray tube, or the X-ray circuitry, I should say. It's a low voltage part, right? And that's good news, because if you're sitting there like me and you've got your Polar Pop from Circle K or whatever, and you're just, sipping away at that Mountain Dew while you're exposing all those X-rays, and you happen to spill that Mountain Dew like me all over the operating console, you're not going to get fried with millions upon millions of volts, right? You'll get fried with maybe hundreds upon hundreds of volts and maybe live through it and look a little weird afterwards and be dizzy all the time, but you won't be just like burned down to the fillings of your teeth. Does that make sense? So the low voltage part is that operating console, and it's there as a safety thing. It's a safety thing. Once we get to the step-up transformer, we are talking about high voltage junk, right? Really, really high voltage stuff. This is the kind of thing that if you touch it, you would be vaporized, right? If you spill your Mountain Dew on it, you ain't going to be standing there no more, right? So that step-up transformer is responsible for stepping up the power to this kilovoltage range, right? And kilo means, thousands of voltage range. And it would be significant if you go around drinking your Mountain Dew around the high voltage generator. So being able to locate where that generator is at, and not horseplaying around the generator, probably the maximum amount of horseplay around it is maybe a good game of paper, rock, scissors, right? Anything beyond that I wouldn't do. You don't want to be hanging any posters of Billy Ray Cyrus on there, or whoever you kids are into now these days. So those types of things. I've still not heard this song, Old Town Road, but like literally this weekend, everyone, like 50 people were like, hey, have you heard Old Town Road? And I was like, no, and I'm not going to. I was just like, I hate this song. I don't even like the name of it. I'm sure it's a great song. I'll listen to it eventually. They'll wear me down. But yeah, not a good place to hang up your posters of Old Town Road like everyone's doing now, you know. I don't know what people do with this song. But it is a high voltage portion. So we'll be talking about that. The final thing, the part that, you know, no one should be looking at funny is the X-ray tube, right? Because not only is it high voltage, it's also kicking out radiation, right? So hopefully you haven't noticed any technologists that are like hanging like cup holders off of the X-ray tube or anything like that, but it's there as a safety consideration that we have these things broken up into these sections. Here's kind of another schematic. This comes from a separate textbook by Stuart Bouchon, and this coincides with on page 134 his crappy picture from this textbook. It's probably my least favorite thing about this textbook is this drawing here. Not a very good drawing. This drawing, Bouchon's drawing I like much better. It's kind of the industry accepted drawing. So if you're one of those people who already took the quiz, you've already seen this drawing. That was my bad. Again, like I said, I've been dizzy for a little while, but the quiz has been fixed now, kind of. I hit it.
I was 25.
When I hit it?
Yep.
And I was in the middle. I was like, okay, I'm doing it. And then
I
it was
was
a
like,
connection error.
Sorry, that's kind of I guess I'm glad to know I have that power, but I didn't realize it was quite that radical. I wasn't trying to just like shut you down, but.
Did my Wi-Fi
Sorry, that was me. Short circuit. So this circuit diagram we're going to walk through, right? And we're going to look at each part of this, and I'm going to talk about each part of it. So I don't know if you're taking notes. I will try to tell you what part I'm talking about as it relates to this diagram, and then I'm going to loosely define what it is and why it's there. And my focus is largely on the safety parts of it, plus producing x-rays. So that's the name of the game with this discussion is identifying the parts, talking about how they operate in order to safely produce x-rays, okay? So the very first thing that we've got is a power source. So literally this thing plugs into the wall somewhere, right? Much like your washer or dryer or something or microwave at home. So that's this little doodad here is indicating it's plugged into the wall. Most X-ray tubes are going to be operating at 220 volts, right? You can find some X-ray tubes like the portable that we've got, the old one from Women's, the Siemens. It plugs into the wall and it literally operates off of 110 volts. So it's a battery falling load generator that operates off of just a standard outlet. But most of them operate off of 220 volts. So that's the power source. Now, one of the very next things it's gonna encounter is gonna be a line monitor. This is similar to if you've ever looked around the back of your house and you see the little thing that's telling the power company how much money they can charge you for the electricity that you're using. This is something like that. It's monitoring the line. It's just seeing how much power is coming into the system, right? That's important. It's important for the power to know how much power is coming into the system because power fluctuates. You know, we've probably all had those weird moments, like what they call a brownout, where it's like the power like flickers across the whole city, you know, and then it comes back online, right? I always imagine that like someone has opened up a gateway to another dimension in those moments. That's what I imagine is happening, but probably in more likelihood it's a raccoon that's fallen into a transformer somewhere, right? Because they seem to like to do that. So it's monitoring the power to see are there raccoons falling into the transformers outside, right? If raccoons are falling into the transformer outside, it tells this line compensator to compensate for that. So you've got like different settings, like 1 raccoon has fallen versus 5 raccoons have fallen into the transformer, right? It's basically, so what I'm saying is that line compensator compensates for any fluctuations that the line monitor noticed. So you got a line monitor, monitoring the line, what the power's coming in, what the scene is. Line compensator is like, oh man, a lot of raccoons are falling right now. We're going to bump up the power or whatever. Not many raccoons are falling, so we don't want to fry the circuitry. You'll notice that the line compensator is doing that by changing the power stations on what we call an auto transformer. The auto transformer is talked about in chapter 7. It operates off of the principle of self-induction. Which means it only uses one coil of wire. So that's the fancy way of saying it only uses one coil of wire. So depending on where we've tapped that coil of wire depends on it. That's how much power it will deliver. All right. So the very next thing, so we've had power in, line monitor, line compensator, to the auto transformer, which I said operates off of self-induction, and it only has one coil. It is a transformer, but it only has one coil. Two things so this is still within the control console, but two things that are going to be hooked up to that auto transformer are the KVP major selector and the KVP minor selector. Now, that's one of the reasons I like the old equipment in our lab, what I call the honeymoon suite, right? The honeymoon suite for me is the smaller room, and the presidential suite is the larger room, right? In the honeymoon suite, you actually have two different dials on the KVP side. You have a KVP major selector and a KVP minor selector. So, the KVP major selector and the KVP minor selector are wired up to the auto transformer. So I'm going to follow out the KVP track first, and then I'll come back and I'll follow out the MA track, because they're kind of two separate tracks running in parallel. Okay? The next thing that we're going to see on the KVP side, and this is still in the operator console, is going to be the KVP meter. This means that the KVP meter is a pre-reading meter. It's not reading actual kilovoltage peak. It's saying what it would be once we apply that to the step-up transformer. So it's reading it on the low voltage side, pre-reading it and saying this is what that would translate to once it hits that step-up transformer. Okay? That's the KVP meter. It's a pre-reading meter. The other thing that we have within the control console is this timing circuit and selector. So here's where we can set the time for the exposure. And this is a common point of confusion for a lot of students, right? So I'm going to spend a little time on the timing circuit, right? And you are probably thinking, whoa, Mr. Roberts, you're a little bit too dizzy. You can't fool me. I know that time is related to mass, not KVP, right? And you are right. Time is related to mass, not KVP. But the way that I control the time is by how long I've got the anode energized. So this timing selector is determining how long the anode is going to be positively charged. I just love watching you pass this stuff around. I'm going to keep passing. Next thing will be like a cinder block. I'll be like, this is actually part of the X-ray tube, the cinder block here. This kind of bag of goo, I made this. This is part of the X-ray tube. I love it. This is just my son's laundry. Just pass my son's laundry around. I saw that. You smiling about it. Here's a really sharp razor. Just be careful with it. All right. So the timing piece is controlling how long the anode is energized, and so that controls how long the electrons are jumping across the X-ray tube, right? So it's on that KVP side, the registry. Those people who drive Honda Accords and live in St. Paul, Minnesota, they know that, right? And they love to ask you tricky questions about that. So guess what? I'm one of those guys. I'm actually infiltrating the ASRT. I drive a Honda, and I would like to live in Minneapolis, St. Paul. So I'm one of them, right? If you haven't figured that out yet. And I like to ask questions about this too, right? Because it lets me know, do students really understand that the time that we're measuring is how long the anode is energized. That's the time in which X-rays will be produced. So all of that is on the control console, the low voltage side of the KVP track that we're following out. The very next thing that we hit is what? We've just jumped into the high voltage section, so any guesses what this Charlie Brown haircut thing is that we've just hit right here? It is step-up transformer. Once we just stepped up, we are no longer in a low voltage section. We stepped up the power. And we are now in a high voltage world, right? This is the place where we're not hanging up our Billy Ray Cyrus posters, right? So the high voltage section, one of the first things that we will hit on this side is what we call a rectification circuit, or I don't know what we're going to call it, the rectification diamond. It's always drawn as a diamond. And these little symbols inside the diamond are diodes, right? Now, we talked a little bit about diodes. We said the X-ray tube is actually a diode. And all you need really to know about diodes is that they only allow power to flow in one direction. So the name of the game now that we've passed the high voltage transformer is we no longer need alternating current. We needed the alternating current to use the transformer. And now that we're past that transformer and we have all the power that we ever dreamed of, right? We no longer need alternating current. We want direct current. Because we cannot pass alternating current through the X-ray tube, it would explode, right? Well, I don't know what it would do. It might open up the portal to the other dimension and cause the brownout. That's another guess. Or it might be the reason why, it might be the place where all the raccoons come from that are falling into the transformers. Another guess. It becomes very theoretical at that point. But we do not want to be passing alternating current through the X-ray tube, right? We want direct current, right? So that's why we pass it through rectification. We'll talk more about it in a second, but we're going to alter the waveform now. We're going to get kind of weird with waves and stuff. Change the waveform. One of the last things that we've got here is an MA meter, right? That's where he's located it, at least, and that's where it's commonly drawn, is there at least on some side of the high voltage section. I'm not really exactly sure why. I probably should know why, but that's just generally where it's placed. Sorry. Final thing that we've got, once we've got the power rectified, we can head to the X-ray tube, the anode side. So the kilovoltage peak now feeds into the anode side of the X-ray tube. So that's that top section. Now let's look at the MA part, the milliamperage part. The first thing that we're going to hit after the auto transformer is an MA selector. And you'll notice the MA selector has these little Charlie Brown sweater things next to it. For those of you who weren't trying to hit each other or hit Fallon with the control console, you may have noticed that on the MA side, there was resistors. That's what that means. Those are resistors. Those little squiggly line things right there are resistors. It's not Wonder Woman. So the resistors are there because we are working towards stepping down the power. We're going to go from the MA selector directly to generally a focal spot selector that lets us choose if we're using the large or the small focal spot, and then a step-down transformer. The step-down transformer steps down the voltage, and in the process of doing that, steps up the amperage. Yeah. The step-down transformer steps down the voltage, but it actually winds up stepping up the amperage. Well, we just moved from, that's a good question. When we moved from MA selector over to the step-down transformer, we've kind of loosely moved over to the high voltage section. Yeah. It's no longer happening in the control console. So the important thing here is that we've stepped down the voltage, stepped up the amperage, increased the amperage. And if you remember, the amps are a measure of current, right? It's how much water's flowing through the garden hose, right? So I've just said we kind of reduced the pressure while increasing the flow, right? But we are going to use that increased flow to produce friction, right? So if you can imagine, what we're doing is we're kind of funneling it towards the cathode. The cathode is this little tiny filament, and I'll pass the X-ray tube around in a minute. No, I'll leave it in the back, but you can go look at it because it's pretty heavy. This filament is very small, and it is made out of tungsten because it has to be able to release a whole lot of heat. When we turn it on, it's going to glow bright red. So when I hit the rotor switch, right, the rotor is going to start spinning on the anode, and the filament's going to start heating up, right? And as it's heating up, the reason it's heating up is because I've stepped up the amperage, I've stepped up the current, and I've increased the friction because the current's trying to run through this little tiny filament. So there's so much friction inside that filament, it does two things, or actually three. It starts to glow, number one. It gets really, really freaking hot, number two. And it starts to emit electrons. The electrons are trying to figure out some way to get past this ridiculous filament. They are trying anything. They're even being boiled off into the air. The electrons are being boiled off. So the fancy word for this is thermionic emission. Thermionic emission is now occurring in the filament. Ms. Smith, you had a question?
Yes. So, like with the portable, you have, the button, and it has a rotor on it.
Yeah.
And it goes all the way down. So when you press the first part of the button down, the rotor, as they call it, of the soda, that's when it's blowing and gets hot.
Yeah. If you were to see inside the X-ray tube at that moment that you're holding down just the rotor, the anode is starting to spin very, very fast. I mean, it's spinning like next week maybe I can bring in I have this really fast circular saw that spins really fast, but imagine it's spinning very fast, like 3,000 rotations per minute. So it's spinning really, really fast, and on the other side, on the filament side, it's starting to glow bright red, and it's getting really, really hot, right? That's all that's happening, though. It's spinning really fast on this side, and it is burning like the sun over here.
So then when you press the button all the way down, it's just spinning.
Yeah, when you hit all the way down, you energize this anode. And so now that it's energized, all the electrons try to jump over there. It's easier for them to jump across that gap than it is for them to try to get down the filament. So they're going the path of least resistance now is to just jump over towards this positive charge. But yeah, we'll look at videos on YouTube real quick, and you'll get a chance to see what it looks like when this thing is glowing. It glows bright red. It's very hot. And the term for that is thermionic emission. It's emitting ions or electrons through heat. The exact same thing is happening, interestingly enough, when you toast your bagel or whatever, right? When you push down the toaster oven, thermionic emission is what's occurring inside the filaments of the toaster. We're just doing it at a much hotter level inside the X-ray tube. So if you're like completely lost, like, oh my goodness, this is miserable, I'm miserable, he's miserable. Let's just, if we can remember this, the control console is the safety first place. You cannot get the fillings, yourself fried down to the fillings with the control console. The high voltage stuff is the hot stuff, right? And then the filament circuit is where the magic happens. It's where the magic happens, because we described how this thing's going to glow bright red, anode starts spinning, and then boom, the magic moment, right, when the X-rays are produced. That's helpful. It's helpful to break it down, but if we're really kind of wanting to be careful, I would acknowledge the work of Janet Jackson in her research into X-ray tubes with her song Control. When we are in the control console, we need to understand that these things are there with us, right? The line monitor, the auto transformer, the line compensator, KVP selector, MA selector, timing circuit, and time selection. So you might be someone who's more visual and you like the diagram. You might be someone who's more auditory or more verbal, and you just need to see it listed out. This is pretty much repeat, right? Just kind of pointing us through that. And tell you what, why don't we watch a little bit of this music video? I can see some eyes glazing over, and this is a great music video. See this next clip, although it is one of my favorite clips from any Simpsons episode ever, where Homer tries to convince Bart that he's not gay, and so he takes him to the Steelworkers Union, and it turns out all the steelworkers are gay, but Homer doesn't realize it. Pretty great scene, but I always think about so Homer's there as they're breaking into, like, I don't know, YMCA or something, and this guy comes by with a vat of molten lava or metal or something. He says, "Hot stuff coming through." But anytime I see that, I always think about the high voltage section of the X-ray tube. So this is anytime you see step-up transformer, just imagine that shirtless construction worker with the molten stuff, hot stuff coming through. Yeah, that's what we're talking about. Everything after that, you're going to get burned, right? You're going to get burned by the disco lights or something. So, step-up transformer on, we're talking about the high voltage section of the X-ray tube circuit. So, from the step-up transformer, we're running directly to the rectification circuit and then to the anode. On the MA side, we've just got the MA meter. We've kind of like jammed it into the high voltage section just because I'm not sure where else to put it, and then the X-ray tube itself is a high voltage thing. So still kind of continuing with the big picture level, we've got the filament circuit, which is kind of, I struggle with where to place this one, right? It is still running power to the X-ray tube, but it does involve a step-down transformer, right? So just understand that it is stepping down the voltage in order to increase the amperage. And what electricians tell me all the time is, it's not the volts that'll kill you, it's the amps, right? So I don't want to be touching this one either. So filament circles out there, step-down transformer, the focal spot selection, and the actual filaments, which we talked about, are what's going to glow red and lead to the magic occurring. That's why I chose for the next music video the Cars' Magic, which is not probably the best song by the Cars, but the music video is really weird. Sure, if y'all want to.
Yes.
You want to? All right, let's watch it. The filament circuit is where the magic occurs, right? It's where the magical occurs. So I'm going to skip over the, we can look at Breakin' later on. I will play a section of the trailer for Breakin' 2, the Electric Boogaloo official trailer by Harry Caesar. Really great movie. But we'll wait on that until I give you the actual activity. Before we jump into the activity, though, I do want to talk about waveforms. And if there's a section where there's a tendency for students to glaze over, this is probably it. So the circuit stuff, I feel like that's a real thing. We're really talking about it. I can pass around stuff. This stuff is weird. And what it's dealing with is what we've learned in terms of waveforms, that alternating current is dealing with a waveform. So if we look on page 122 in our textbook, we're going to start using the textbook more. I'm going to just kind of walk you through it with the textbook, and then we'll look at a diagram. So there's some stuff we should underline here on page 122. We have a direct current waveform that just looks like, I always imagine like a butte in Utah, right? Just like a cliff or something, like the thing from Close Encounters of the Third Kind. Versus alternating current is this wavy thing. That's what I mean by waveform. It's a wave, right? And there's some important stuff here about this wave. On this little illustration, it tells me it's a 60 hertz wave because power waveforms in the United States of America are 60 hertz, right? Versus if you go to plug your hairdryer in Germany, it's a different hertz. So you'll hurt yourself. That means that every second, there's 60 cycles of this waveform. Well, what's a cycle? A cycle is a wave up and a wave down. That's a cycle. So there's 60 waves up and there's 60 wave downs every second at 60 hertz. So that's what it tells me down below, and I've underlined it. 60 pulses flow backward towards the plant. 60 pulses flow from Pickwick Dam, and 60 pulses flow back to Pickwick Dam every second as those big turbines are spinning. So while everyone's out there jet skiing or whatever and listening to Janet Jackson, there's at the dam is where the work's actually getting done, right? And what the work is there's these big hydroelectric turbines, and they're spinning big magnets. And those magnets spin at 60 cycles per second, right? And that's inducing power in the wires that are wrapped around in the magnets, right? So he tells us that on page 123. If the magnet spins 60 revolutions per second, 120 pulses of electricity will be produced for every rotation of the magnet. And you're like, well, where did you get 120 pulses, right? Well, the pulse is any one of those waveforms. So the cycle is a wave up and a wave down. In the cycle, there's two pulses. There's a pulse up and there's a pulse down. There's a pulse towards the dam and a pulse away from the dam. Have I lost anyone so far? That is alternating current here in the United States of America. And I probably shouldn't know this, but for whatever reason, I do know that there's also a Predator station out there somewhere, like a secret military base where they fly Predator drones close to Pickwick Dam. Yeah. So that's the other work that's being done out there by Pickwick Dam.
What do you mean?
Predator drones, drones that blow things up in other parts of the world. So that's what's illustrated here on page 123. The magnet spinning and inducing the pulses in that wire. It's as simplified as possible. We're just spinning big magnets, and those magnets, through induction, are inducing pulses of electricity that are used to power this computer and y'all's computers and everything here in the city of Memphis. That's great. And we're going to use that. We're going to use electromagnetic induction. So that's power generation. We can also use it to run engines, right? So if we're spinning the magnet, we can produce power. If we're using the power to spin a magnet, then we're producing mechanical energy. And so that's what we mean by electric engine. So if you're doing this versus that, on one side we've got a power generator, and on the other side we have an engine. Those are two different things, right? Well, where do we use an engine or a motor, right? We use it to spin the anode. So in this case, we have a stator, a wire coil that's just staying there, and it's pulsing power at a rotor which is rotating now, right? So that's an example of a motor. So we've got them right next to each other on page 125. We've got generator on one side, spinning the magnet, inducing a AC current in the wire. And on the other side, it looks very similar, but that's a motor. The coil, the power's passing down the wire and it's spinning the magnet, right? So on one side inducing power, on the other side spinning the magnet. That's what that illustration is there for. That's great. That's helpful, actually. I know it's not terribly exciting, but it is very, very helpful, right?
That's great.
That's really great. It is completely crap if we're trying to make x-rays, right? I'm just putting that out there. We do not want these waveforms. They were there, they helped, we were able to make the power, and we were able to spin the anode with the waveforms. But once we get to the moment of magic, where the guy steps out onto the pool, no waves. We don't want no waves. Don't give me no waves, right? To get rid of the waves, we have to apply rectification, right? So remember I talked about that weird diamond on the high voltage side? That's where the diamond comes in. Okay, so we're going to start chopping up this waveform. We can chop it up a bunch of different ways. The simplest way to chop it up is a half wave, right? That's what's illustrated on page 138, half wave rectification. It means that we were able to cut out all the negative, all the power going back to Pickwick Dam. We got rid of all of that, and we kept all of the power coming from Pickwick Dam. But if that were the case, it would mean that every second we would get 60 pulses of power. Because we got rid of half of our pulsing, right? We've only got 60 pulses, just the power coming from Pickwick Dam, right? So that is this illustration here. That is half wave rectification. We chopped off the part of the wave that we didn't like. So if you're wondering, like, why do we care about the power coming from Pickwick Dam versus the power going to Pickwick Dam? We only want electrons jumping in one direction. We want them jumping from the cathode to the anode. We do not want them jumping from the anode to the cathode. So in this schematic here, we've got electrons jumping from the cathode to the anode 60 times every second. All right? That is half wave rectification. Now you'll notice they don't always have a crap load of energy, because the wave kind of starts at 0 and then it goes up to a peak and then it goes back down to 0. So that means that it's got a lot of ripple, because it starts at 0, it goes up to a peak, and then it comes back down. So every time my hand comes back down, we're creating a ripple. That's 100% ripple. So this single phase rectification process of a half waveform, 60 pulses every second, 100% ripple. If you know that, you're good, right? All right, well, why are we wasting power? Is there a way that we can get that power going back towards Pickwick Dam and use it, right? And there is, yeah, that's what we're doing when we do rectification. We can flip the waveform over the 0 line, and then we get full wave rectification. It looks like this on page 139. It looks like the McDonald's sign. So the McDonald's sign, we flipped the negative part over the x-axis, over the 0 line, and now we have 120 pulses per second. 120 pulses per second, 100% ripple. So it means we're getting more x-rays, right? But they have varying amounts of energy. All right. The other reason I wanted to show you that Ridiculous Cars video is because they're kind of singing in rounds, right? Like he sings, "Uh-oh, it's magic," and then the band sings, "Uh-oh, it's magic," and they're singing in rounds, right? Like row, row, row your boat gently down the stream, something like that. We can take things out of phase and make this start to sing in rounds, right? Which is what we're doing when we start to mess with the phasing, right? So this is fully rectified, 3 phases. A few things that I have underlined here is he does offer some explanations around how the phasing works. I wouldn't get too much into the weeds of it, but basically on page 139, right here, it says 3 distinct sets of electrical current that are sequenced over time such that the pulses of electricity overlap each other. He has a nice little illustration of it right here, right next to it. So we're starting 1 round, 2 round, 3 rounds, and we're getting these phases of pulses now. So each second now, 360 pulses are being produced. Where did I get 360? I took 120 and I multiplied it times 3 for 3 phases, right? So I took 120, I multiplied it by 60, now I have a 3-phase. I can throw even more pulses in there, right? But one of the significant things that's happening now, as I start to phase this out, you'll notice what happened with the ripple. It significantly decreased the ripple. Where did the ripple go? Well, you'll notice with this illustration here at the bottom of the page, when we started phasing it, no longer is it going all the way up and coming all the way down and all the way up and coming all the way down. Because as this one goes all the way up, as it starts to come down, the next one that was coming up starts to come up, and the next one that was coming up starts to come up. So they even each other out across the top. So it significantly decreases the amount of ripple in the waveform. It gets rid of the low energy parts. So with 3-phase 12 pulse, 4% ripple. With 3-phase at a high frequency, less than 1% ripple. Here's an illustration of them all side by side. Right? Half wave, well, we just got rid of the lower part, 100% ripple still, 60 pulses per second. Full wave, we flipped the lower part, the power going back to Pitwick Dam, we flipped it over the 0 line. Now we have 120 pulses per second, but we still have 100% ripple. 3-phase 6 pulse, because of phasing now, we've got 360 pulses per second, right? 14% ripple. Once we get to 3-phase 12 pulse, we've got like 720 pulses per second and 4% ripple. It means we've got more power, right? Each time we're doing this, we're increasing the amount of power. Now, I know this seems really, really nerdy, right? And really, really kind of abstract. Let me talk to you real quickly about where this translates to your clinical practice. Because you're going to be at some clinical sites where you actually have to think about this. I'm not going to name any names, but there are some clinical sites where we every year we have students come back and say, man, they're using a really high mass at this site. Like, I don't know why. Like, it's like 10 times what I use at other places, right? And they say it's perfectly fine. The pictures look the same. The exposure indicator's the same. I don't know why they're exposing the patients so much, right? Well, that machine, right, that they're using does not have a full power generation behind it, right? So in order to compensate for that lack of power, they have to increase the mass, right? So to compensate for that, that decreased power, they're increasing their mass to compensate. A similar thing can happen if you have a machine and one of the rectifiers goes out. If one of those diodes go out on the little diamond, you just went from full wave rectification to half wave rectification, just like that. So if one of those diodes go out on the diamond, you just went back to half wave rectification, and guess what? You're going to have to double the mass on everything that you're shooting. You're going to have to double the mass on everything that you're shooting across the board until they replace that one diode. There's other power implications that he talks about here in the textbook on page 139. This impacts contrast. I know that we haven't defined contrast yet, but if we see right here at the bottom of this paragraph here, the last full paragraph on the left side of the page, this provides a higher overall penetration for the X-ray beam and more exposure to the detector plate. So anytime we see increased penetration, just know, for right now, just memorize this, it means decreased contrast. If we see increased penetration, it means decreased contrast. So I've drawn just in the margin, arrow down contrast, right? So we'll be coming back to that. We'll be revisiting this. Okay. All right. Last thing we're going to talk about before a flock of seagulls is exposure timing. This is on page 141 in the textbook. What we're talking about, in essence, is mostly automatic exposure controls. Now, we can still use manual technique, right? On your portable work, a lot of times you're having to use manually set mass, right? Commonly, these are electronic timers. And a lot of times you don't even see what the timer is, you just dial in the mass, right? And it just calculates the mass. And the way it does it is it wants the maximum MA at the shortest amount of time. And that in general is the ideal technique for almost every patient that we shoot, is the maximum MA at the shortest amount of time, right? The maximum MA at the shortest amount of time. But time is really of the essence for a lot of what we do, right? It's there in time, distance, and shielding, right? It's how we control exposure, is the amount of time that the X-ray tube is activated. And we recognize that there's a lot of variables in patients, right? So that's why I want to point us to figure 816 on page 143. This is how mostly time is controlled when we're shooting in the department. And it is why techs, if you've ever been with a tech and they're grumbling about going to shoot a portable, they haven't shot a portable in a long time. Has that happened to anyone? Yeah, okay, it's coming. Because what they're not sure about when they go out to do the portables is what the mass should be, right? Because they've gotten so accustomed to just having the photo timer figure out what the time should be, right? So they're not sure what the mass should be because they've used an automatic exposure control. What automatic exposure control does is this thing here that looks kind of like Mickey Mouse on the Bucky, right? Underneath each one of these little parts of Mickey Mouse's face is an ion chamber, right? That ionization chamber is registering how much exposure is reaching that little air chamber, right? You can't see it on the X-ray. A lot of times it's just like made out of plexiglass. It has a gas inside of it, and every time an X-ray hits the gas inside of there, it registers that strike, right? After it gets enough strikes, it stops the exposure. So it automatically controls what the exposure is to the patient, what the exposure is to the image receptor. So that's what this illustration here is showing us. It's showing us the X-ray tube. That lump of gelatin there is supposed to be the patient, I guess. And you'll notice between so the patient's laying on a table, and between the patient and the image receptor is an ion chamber. Between the patient and the image receptor is an ion chamber. And so as X-rays hit the patient, some of them are attenuated, some of them go through. They then go through the ion chamber. They start to cause ionization inside the ion chamber. Once enough ionization is reached, it tells the exposure to stop. It interrupts the exposure. So if we want to change the density of the exposure, we use what's called a thyrotron. So we see the ion chamber is connected to this thyrotron here, right? And this presets the amount of charge the capacitor can hold. So Once the capacitor hits its ceiling, the exposure goes off. I can tell the capacitor to be bigger or large, or bigger or smaller, and that controls the length of time of the exposure. So that's what we call density controls. They're linked to a thyrotron. If you've ever seen the tech kind of bumping up the density controls on the AEC, that's what they're doing. They're controlling how this capacitor is working that's receiving information from the ionization chambers. So I would review that information closely. It's a separate circuit, but it's connected to the X-ray circuit. All right. I have slightly changed the activity, but not the playlist for the activity. So I'll still play you some 80s music while y'all are working. You may work independently or you may work in a team.